Historically, this building type often featured relatively simple plan geometry, regular and not overly extensive exterior fenestration, as most important structurally, a relatively uniform distribution of shear walls of roughly equivalent stiffness. The code provisions relevant to this building type have implicitly assumed these features. Traditional analysis techniques utilizing flexible diaphragm assumptions and floor-by-floor shear wall stiffness distributions were and continue to be adequate to analyze regularly configured buildings of this type. However, many of these buildings currently being constructed now do not possess relatively simple plan geometry, have extensive exterior fenestration, and irregular distribution of shear walls at some levels. These buildings are growing increasingly complex as architects attempt to increase density, optimize the amount of natural light each unit enjoys, and provide articulation at the exterior walls. Note the scale and plan configurations of these typical wood mid-rise light frame residential buildings. And here is a site plan of a typical current multi-unit residential project. Note the differences in plan geometry between the multi-story residential buildings and the retail buildings in the bottom left-hand corner. So when the structural design of a wood multi-unit light frame residential building commences, there are many decisions that have to be made which will affect the design. What type of framing are we using? Joists or I-joists or sawn lumber? What direction will the framing be running? Can we get mechanical ducts into the joist bays? In which direction are the units to be vented, horizontally or vertically? What are the acoustical requirements of the floor and wall assemblies? What structural elements need to be fire protected? And of course, where are the shear walls? Do they conflict with the mechanical plumbing walls or mechanical systems? There are a lot of decisions that need to be made relatively early in the design process, most of which will affect both vertical and horizontal lateral force resisting system elements. And note how this building type is composed of many distinct structural elements that make them difficult to analyze accurately. So let's go through some of the challenges that engineers face when designing buildings of this type. How should we characterize the building's diaphragm behavior? Should we use a flexible diaphragm analysis or rigid diaphragm analysis? What are the current code requirements? Wood mid-rise light frame residential buildings are wood shear wall buildings, and I'm sure most engineers could design it for strength, but what about drift? If our building is adjacent to an existing building or requires a seismic separation joint, how does one calculate the appropriate size of the building separation? To address these challenges, we need to understand the unique characteristics of this building type and the relevant code provisions. An implicit assumption of the code is that wood mid-rise light frame residential buildings have uniformly distributed shear walls of approximately equivalent stiffness. However, this assumption is often violated at the exterior and sometimes at the first floor level. Here's a typical plan for this building type. Note that virtually all the units only have one exterior wall. There is a perpetual negotiation at the exterior for reducing walls to maximize windows and the need for natural light versus lengthening walls for the vertical lateral force resisting system. These buildings typically consist of a series of individual residential units divided by corridor and party walls. These walls function as the building's primary shear walls due to their length and regularity, as well as their lack of penetrations.